So parameters don't depend on time, but they are things that can vary from situation to situation. Okay, so, for example, the first model we studied for population growth, the Malthusian model, dp dt equals k times p. T is your independent variable, p is the variable that depends on t, and k is a parameter. It's just a constant that's going to be different for different populations. So we would expect k to be much larger for, say, a rabbit population than a human population. So our goal today is to study how the solutions to a differential equation change as you vary the parameter. So this is often a really important question to answer when we're using a differential equation to model a real-world thing. So the book gives an example of writing a differential equation that will model the motion of a bridge over time, and it has a parameter in it that accounts for the mass the bridge is holding, right? So you want to know if the solutions change based on the number of cars that are on the bridge. Really important to know. All right, so we're going to do an example together, walk you through it, and then I'll give you another one where I walk you through it on the paper, and then you'll do one totally on your own. All right, so I have the differential equation dy dt equals y squared minus 4y plus mu. Okay, so mu is going to be my parameter. It's that constant that changes. So I want to see what the solutions to these differential equations look like and how they depend on mu. So this is really a family of differential equations. It's a different differential equation for every value of mu, for every constant that I tack on the end there. So I'm going to start by just looking at the parabolas that are defined by the right-hand side of the equation. Y squared minus 4y plus a constant is just a quadratic function. So I call this the f sub mu is how I refer to the family of differential equations where I take on all different values of mu. And so f sub 0 is the function where I replace mu with a 0. So this is going to be y squared minus 4y. So I want to graph this parabola. Y squared minus 4y. So on my axes, I'm going to have y as my independent variable, and f of y is my output. So what does this parabola look like? A cup? Yep. Where's its vertex? Mu is 0. Mu is 0 in this case. For this particular one. How do you determine where the minimum of a function is? It's at 2. How do you know that? Okay, so that's one way. If it's a parabola, you can do negative b over 2a, which comes from taking the derivative and setting it equal to 0. So let's do it that way because it's a more general approach. For in the event we don't have a parabola where we don't have a nice formula, negative b over 2a. So to find the minimum of a function, we take the derivative, which would be 2y minus 4. We set it equal to 0, and we get y equals 2. So at y equals 2, so I know that the minimum of this function is going to happen at y equals 2, right? Set the derivative equal to 0. That's how you find where the minimum occurs. How do you know what the minimum value actually is? Plug it back in. Yes, if I take a 2 and I plug it in here, 2 squared is 4. 4 minus 4 times 2 is negative 4. So 2 negative 4 is the minimum for this function. And then some other key points that I might like to graph could be zeros. the x and y intercepts. Yeah. So I know that it's going to go through 0, 0. The y-intercept is 0 because f of 0 is 0. And so then my other x-intercept, 4. So that should be pretty good. We can graph that now. So everybody is clear how I got the key points in this parabola. To find the vertex, take the derivative, set it to 0. That's where the vertex is along the horizontal axis. Take that point, plug it into the original to get the y-coordinate, or the vertical coordinate. And then the x-intercepts you just find by setting the function equal to 0. Okay, so this is a graph of dy dt when mu is 0. So I'm going to label it, this is f0 of y. All right, so how are the parabolas y squared minus 4y plus mu related to the graph I just drew? Shifts up and down. That mu is just going to be a vertical shift. Vertical shift by mu units. All right, so we're going to find the bifurcation value. So once we go through a couple more questions, you'll understand why we're looking for this. Okay. All right, so on the same set of axes, we want to graph the parabola in the family y squared minus 4y plus mu that has its vertex tangent to the horizontal axis. Okay, so it's going to look just like the thing I graphed, but I want its vertex to be right here, right? So I'm shifting my whole parabola up 4 units. Good. So that means that this point 0, 4 would go to, 4, 0 would go to 4, 4. I'm going to have 4, 4 and 0, 4. And here's my parabola. And this is, I don't know which one that is. I want to know what value of mu will give me that. 4, yeah, because I'm shifting it up 4. So this is f4 y. Okay, so yeah, that was simpler to answer than I realized. But let's say it's not a parabola. Yeah. What has to be true if we're going to make the vertex tangent to the horizontal axis? What has to be true about f of y and f prime of y? They both 0. Because this one is because we're touching the x-axis, right? I should stop saying that. Tangent to the horizontal axis. Because the horizontal axis is really y in this case. And f prime has to be 0 because it's the minimum. So they both have to equal 0. So this is how we could figure it out. I could say, well, f sub mu of y is y squared minus 4y plus mu, and f prime is 2y minus 4. These things both have to be 0. And I have 2 equations with 2 unknowns, y and mu, so I can figure out what they both are. So here, solve for y, and I get y is 2. Plug a 2 in here. Solve for mu, and you get 4. No, positive 4. So we were able to answer this just by thinking about transformations, but you can also do it with calculus. Set the derivative and the function to 0. All right, so we're going to call this value mu equals 4, call it b for the bifurcation value. It's where interesting things happen. You can do it with a maximum as well, yep. Then there will not be a bifurcation value. Yep. Yep, so the bifurcation value is the place where the function on the right-hand side of a differential equation goes from having where the number of solutions, number of zeros changes. So we go from 2 to 1, and then as I move this up, continue to shift it up, I'm going to have 0 x-intercepts. So that's my bifurcation value. So yes, if your function is always increasing or always decreasing, you can shift it as much as you want, and you'll never change the nature of the solutions. Okay, so I want to choose two nice numbers, one a little bit bigger than 4 and one a little bit smaller than 4. What do you think? 5 and 3, I like those. Okay. On the same axes where we've been drawing our parabolas, I want to draw the y squared minus 4y plus 5 and y squared minus 4y plus 3. So I'm going to add two more parabolas in here for mu being 5 and mu being 3. So if mu were 5, I would shift this up one more. And then get a parabola like this. And I should not have crossed those. So this is this red one is f sub 5. This blue one was f sub 4. And then I'm going to do one for f sub 3 where mu is 3. So that's shifted up 3 from the green from the original. So it's going to be like this. Up 1, 2, 3. Black one. This is f sub 3. So I have parabolas for all several different values of mu. And my parabolas below the bifurcation value, which was f4, so the 3 and the 0, both have 2 x-intercepts. At the bifurcation value, it changes, so it only has 1. And then after the bifurcation value, we have no x-intercepts. Okay, so what I want to do is I'm going to draw a bifurcation diagram, which is just a bunch of phase lines. Okay, so last class we learned how to draw a phase line. Now, so we learned how to draw a phase line for a single differential equation. We have a family of differential equations here now. I want to draw a phase line for several members of the family. In fact, the members that I just graphed. Okay, I want to draw a phase line for each one. So I'm going to draw a set of axes. Y is going to be my vertical axis. My horizontal axis is going to be mu. So I'm going to draw a phase line for several different values of mu. So I want to draw in vertical lines mu equals 3, 4, and 5. Okay, so now I want to use my parabolas, which are graphs of the right-hand side of the differential equation, to draw in the dots and the arrows that will make these into phase lines. So let's start with the 3. Look at the parabola for F3. That's this one drawn in black. Okay. Where are the equilibrium points? 1 and 3. Yep. Places where my function equals 0 are at 1 and at 3. So 1, 2. So at 1 and at 3, I have equilibrium points. Now I want to know between those two is the derivative that I've graphed positive or negative? Negative, so I indicate that with a down arrow on my phase line. And on either side, it's positive, right? So I put an up arrow on either side. Oh yeah, sorry. Okay, so I did a phase line for that particular differential equation. Now I want to do phase lines for my other two. At 4, I only have a single equilibrium point. Where is it? 0. Is it at 0? 2. It's at 2. Right? The blue one, right? F4, it has a single equilibrium point at y equals 2. Y equals 2. And the derivative is always positive on either side of that equilibrium point. So I'm going to put in my equilibrium point at 2 and put up arrows on either side of it, because the parabola is always positive. Okay. And then for the 5, F5, do I have any equilibrium points? No, because it doesn't. That parabola never crosses the x-axis, so I have no equilibrium points. And it's always positive, right? Because we're always above the x-axis, so I have just an up arrow on the whole line. So this is the start of a bifurcation diagram. So this lets us see how the behavior of the solution changes. You can see that any phase line to the left of 4 is always going to have 2 equilibrium points, because those parabolas will always have 2 x-intercepts. And then as we shift the parabolas up, 4 is sort of the place where things change, where we change from having 2 equilibriums, one a source, one a sink, to only having 1 equilibrium point, which is a node. All right, so yes. So the term equilibrium point corresponds to an equilibrium solution to the differential equation. And when I'm drawing a phase line, I call it a point because that's how we represent it. It means an equilibrium solution to the differential equation. So these phase lines set the pattern for all other phase lines. We're going to add 4 vertical lines to the diagram that we just created that alternate with the 3 lines that we already have. And using the lines we already have and our knowledge of what these parabolas will look like based on transformations, we're going to draw in the arrows and dots to make the lines into phase lines. So we go back over here. I'm going to add 4 lines, alternating with where I already have them. So maybe I'll put one here at 2. One here. Okay, so if I have a phase line at mu equals 2, for mu equals 2, how many equilibrium points will it have? 2, yeah, if we go back and look at the parabola, mu equals 2, It would be shifted up 2 from the green one. 1, 2. And it's going to have 2 equilibrium points, right? Somewhere between 0 and 1 and 3 and 4. So I'll put my equilibrium points in the approximate place where they go. Somewhere between 0 and 1 and somewhere between 3 and 4. And between them, between the 2 equilibrium points, my derivative is negative. Outside, it's positive. So at 4.5, oh, sorry, 3.5. 3.5, where are my equilibrium points going to, how many am I going to have, first of all? 2, because I haven't gotten to 4 yet, but they're going to be closer together, right? Because they get closer and closer together until they are single point at 4. So here I'm going to have 2 equilibrium points, but a little closer together than they were before. In between, negative. Outside of them, positive. I know. Yeah. So I am creating, my equilibrium points are forming a parabola. And then once I get past 4, all of my parabolas that I've been graphing are going to have no equilibrium points, no x-intercepts. So all of these other guys are just going to be positive, no equilibrium points. So this is called a bifurcation diagram. And this is where my differential equation, my family of differential equations, we can see how the behavior of the solution changes. And I go from having 2 equilibrium solutions, one a sink, one a source, to having one that's a node, to having none. And the place where the transition happens is called the bifurcation value. So we say dy dt, right, our differential equation, our family of differential equations, bifurcates at y equals 4. So we say it bifurcates at y equals 4. You can also say has a bifurcation value at y equals 4. So the nature of the solutions changes. Yes, thank you. Mu equals 4. So mu equals 4 is a critical value of the parameter. So often, differential equations are used to model real-world things, and it's very important to know if bifurcations happen in the solution. So in the cholesterol problem that you guys did in quiz 1, there were lots of parameters, and it would be interesting to look at them and see if there's some place where the solutions have a bifurcation, right? Maybe right, N was one of the parameters, the person's natural cholesterol level. So that might have some influence on how many equilibrium points there are, and whether or not it's possible to lower your cholesterol. Okay. All right, so now we're going to use our bifurcation diagram to draw 3 different solutions, because there are 3 different differential equations, one for each value of mu. Draw 3 different solutions using the phase lines that I drew. So I'm going to put in any equilibrium solutions, and solutions that at least one solution in each different region between the equilibriums and outside. So here we'll start with mu equals 3. How many equilibrium solutions were there? 2. And according to the phase line, they were at, what does that look like? 1 and 3. 1 and 3. So equilibrium solutions. And 1, the equilibrium solution at 1 appears to be a sink because my arrows are pointing towards it, which means that any solutions on either side of the equilibrium will tend towards it. And my other one is a source, which means solutions on either side of that equilibrium solution will go away from it. So 1 was a sink, so I can, if I have an equilibrium point here, sorry, an initial value, I will have to approach the sink. And if I have an initial value below it, that also has to approach the sink. And if I start above the 3, it has to go away from, no, the 3 was a source. 3 was a source. So, and then if I go backwards in time, this goes like this. This goes like this. That goes like this. And then for mu equals 4, I had one single equilibrium value at 4. Equilibrium point at 4, which was a node, right? Which means from below, yes, sorry. Equilibrium points at 2, yeah. And it's a node, and my function was always positive, right? So I'm going to be always increasing. My solutions will be always increasing. So they're going to approach 4 from below and go away from 4 when I'm above. So if I have an initial value down here, they have to approach 2, sorry, I keep saying 4, and go away from 2 if I start above. Okay, and then if I do mu equals 5, that had no equilibrium solutions, and which my arrows were always pointing up, which means that the solution has to always be increasing. So no matter what initial value I choose, I know that it increases. I don't know exactly how. It could be concave up, concave down, but it goes up. Something like that. All right, so bifurcation diagrams allow us to solve a whole family of differential equations at once and find out the point of interest, the place where the solutions change nature. All right, so now you guys can try the next one in your groups.